tried some things that many people said was impossible. But we've achieved that, and we wish Hubble the very best.
The Hubble Space Telescope achieved its greatest performance yet, looking for when and how the universe began.
With the Hubble, we made incredible discoveries. We measured the age of the universe. The discovery of dark energy was actually confirmed by Hubble. People argued about whether black holes were in the center of the galaxies. We found black holes everywhere. It told us amazing things. But as we look deeper and deeper and deeper with the Hubble Space Telescope, we come to the end of what the Hubble can see. We just see darkness. We realized we should build the largest space telescope humanity has ever conceived of. This is the next generation space telescope. It's Hubble 2.0. And we have 1,000 people working on this project right now. And that all comes together on a launch pad in 2018. If it works, it's going to see deeper into space than any other telescope in history.
The Webb telescope is 100 times more powerful than Hubble. Telescopes keep getting bigger because the bigger they are, the more light they can collect, and the better the resolution. You know, at some point you build a telescope that's too big to fit in a rocket. And James Webb would not fit in a rocket. So we had to make the primary mirror into individual segments. Learning how to build a segmented telescope, this is new. It's been done on the ground once or twice, but doing it in space is a whole nother set of challenges because the mirrors have to be lightweight. You have to figure out how to align the mirrors in space. You know, we wouldn't have built a telescope this big unless we needed to, and you need to build a telescope this big if you want to look at the very dimmest, most earliest galaxies in the universe. If you took one of the mirrors and you spread it out the size of the United States, there would be no hill or valley that's larger than 3 inches, to give you some idea of just how perfect these surfaces need to be.
These mirrors are going to literally watch the universe light up after the Big Bang. They will help us learn about the beginnings of galaxies, the beginnings of stars, and exoplanets, planets orbiting other stars. These mirrors are going to capture the very first light of the universe.
Observation is everything. Ultimately, science is about observation. It's like Galileo when he lifted his telescope to the stars for the very first time. There's no turning back from that moment. And he looks at the moon. And this was supposed to be this perfect orb. It had rocks and craters and was far from perfect. And then he looked at Venus. It had crescents that changed as they moved across the sky. He looked at Jupiter, and he noticed these pinpricks of light. And as he watched them over the weeks and the months, and realized these weren't stars, these were actually moons in orbit around Jupiter. And of course, he realized that Ptolemy was wrong, Copernicus was right. We were no longer the center of our solar system. The sun was. The church could no longer argue that everything had to be centered around the earth. Observation trumped ancient wisdom. And that's what science does. It makes irreversible changes in our worldview.
At the beginning, when I first came on to work on JWST, wasn't terribly straightforward for me to keep track of which orientation was what. Okay, which direction was J3 and J2 and J1 again? You would sit in a conference room with people and they would grab like a stapler, and go, okay, this is the spacecraft, and then here's my instrument, and then this, and it just seemed a little silly. Which way is it pointing? And so I brought in my Lego set one day and went, build it. Let's build it.
I think everybody wants to do something, be a part of something greater than just what they can do alone. Building something like JWST is that. So what I don't understand is why everybody isn't trying to do it. Trying to be, an engineer, work on these big projects, becoming scientists, I don't know, what else would you want to do with your life?
Hubble Deep Field was a pure discovery. It was, we don't know what's there, let's see if we can see something. The second director of the Hubble Space Telescope said, Hubble is looking deeper and deeper in the universe. I wonder what happens if we just stared at a completely blank piece of sky and just see what we find. And so he decided to point the telescope at a single blank piece of the sky, no bigger than a drinking straw. That's the area of the sky he decided to look at with the Hubble Space Telescope and just stare at that single blank spot for 10 days and see what would happen. A lot of people said he was crazy, he was wasting telescope time, but the telescope was orientated and just stared at that one spot for 10 days with our most sensitive cameras at the time. And to everybody's surprise, when they looked at the image, out of that dark area of the sky came 10,000 galaxies in that single point of sky. Nobody had any idea there was this many galaxies in the observable universe. When you look at the Hubble Deep Field, only 3 of those points of light are stars. Every other point of light in that image is a galaxy. So there are 10,000 galaxies in every spot of the sky the size of a drinking straw. Roughly 100 billion stars in the galaxy. If you do the math across the whole sky, it's 10 to the 22 stars in the observable galaxies. And I'm not going to work out what that is, but it's 10 with 22 zeros. It's larger than even the US debt, That Hubble Deep image is what inspired the James Webb Space Telescope originally.
Someone telling us where to stop?
Slow down, slow down.
Slow down. Slow.
When people think about the telescope, they think of the huge mirror, right? That's the iconic part of the telescope. But this is what the astronomers care about. This is where the data comes from, the detectors and the cameras. All the images and the spectra, all the good stuff. It'll come from there. You know, it's $1 billion worth of hardware in there.
So this is the first time you're going to go cryo-test the 4 instruments all together, put together in one place, and the IEC, which is your instrument electronics compartment, all of it's together. This is the Space Environmental Simulator, and so they're putting it in for thermal vacuum testing. Launch is not the greatest stress for this telescope. It's actually going to the cryogenic temperatures. The temperature we're going to is 40 Kelvin. 0 Kelvin is absolute zero.
What happens at absolute zero?
Oh, the universe stops. All the physics changes at cryogenic. Things that expand, contract, things that contract, expand, for instance. So you don't know how these things are going to do till you get there.
Well, it's roughly room temperature out here. It's just like space on the other side of that wall. What would happen to a human being in this cryogenic?
Oh, they'd die. You would blow up as the pressure goes down, so you'd explode. If you survive that, then when the nitrogen goes in, well, you die of asphyxiation.
Fundamentally, the telescope is a time machine. The telescope is always a time machine because your eye is a time machine. You can see things as they were when they sent light to you. It takes 2.5 seconds for light to go from here to the moon and back. You see the sun as it was 500 seconds ago. About 8 minutes. We're 6 feet apart, so you're seeing me 6 nanoseconds as I was 6 nanoseconds before you see me. So light travels at the speed of 1 foot per nanosecond in round numbers. You see the Andromeda Nebula as it was about 3 million years ago, and that's about as far as you can see without a telescope. But with a telescope, you can see billions and billions of light years out in space, so billions and billions of years back in time. And of course, by now they're much farther away than they were when we saw them. So those things are not there anymore. They have gone on to do something else. Some parts of the universe we'll never see because they're accelerating away from us now. So they're going to accelerate away so far that the light from them will never get here.
As we look deeper and deeper and deeper, we see fewer and fewer galaxies. It is not that we're running out of galaxies. It was the fact that as the universe is expanding and stretching across space and time, its light is being redshifted, and the galaxies from the very early universe are being shifted out of the view of the Hubble Space Telescope.
The Hubble telescope can only see what you can see with your eye, the wavelengths that your eye is sensitive to, plus a little bit of ultraviolet and a little bit of infrared.
Those galaxies are so far away from us that as light travels through space and space is expanding because the universe is expanding, the light gets redshifted. So it changes from blue light into red light as it travels through space.
It's so far away from us and so far back in time, its light only reaches us via infrared wavelengths. The Webb is going to give us infrared eyes, and we'll see a part of the universe we've never seen before.
The Hubble Space Telescope has transformed our knowledge of the universe. But we haven't been able to study the first galaxies that formed in the universe. We haven't been able to find their light. And that's what the James Webb Space Telescope would provide. We can fill in one of the biggest missing pieces. When did the first stars and galaxies turn on? We'll detect the first light that formed from the first stars and galaxies in the universe.
We have enough sensitivity with our telescope and our instruments to detect a child's nightlight located on the moon. You could see things, on the order of a candle, a match, a lit cigarette. I know that if you were to certainly take your radiant heat, which for a human is about 80 to 100 watts, and stick it on the moon, we would easily be able to detect that.
It can even pick up the heat of a bumblebee. That is completely astonishing to me, even knowing that that's our telescope and we built it that way.
Yes, I've heard that. In fact, I was asked about it. I'd have to sit down and do the math very, very carefully. I've learned one does not argue with Nobel Prize winners unless you're 300% certain that you're correct. Although I'm quite certain you can see the nightlight.
I heard about this calculation. I checked it myself. I believe it's correct. Yeah.
If we had the moon here and the Earth 250,000 miles, what we need to do first is calculate the area of the sphere. 4 pi 4 times 10 to the 1 joule per radius, which is 400,000 kilometers. Frequency times 12.5 10 per second squared. Energy frequency times 10 like constant 12.5 is 2 times 10 about 620. Something like 1.5 approximately. 1.5 milliwatts. If our insect were radiating that much, and I'm not an entomologist, don't know exactly how much of an insect radiates, but that doesn't seem out of the realm of possibility.
A bumblebee gives off how much energy?
Well, let's see, it gives off about 50 milliwatts of power.
It does seem reasonable, but we could see a bumblebee on the moon with our telescope.
And 50 milliwatts of power at 250,000 miles is measurable.
Yeah, is measurable.
That's a bumblebee as opposed to a yellow jacket, as opposed to a hornet, but we could collect the light. Should know better than to argue with our chief scientist.
You have to take a time exposure to get something that sensitive. The bumblebee shouldn't move.
The bumblebee has to hold still.
Yeah, and the bumblebee has to hold still. But of course, the most distant universe looks like it's standing still.
Brian, are you ready? Ready.
We don't want the telescope portion of the Webb telescope to see any of the sun. The light that we're looking at are in the infrared. So in order to detect heat signature, infrared signature, it obviously needs to be very cold, or all it's going to measure is just itself, basically. So we need to keep it very cold. And in space, really the only thing that'll heat you up is the electronics that you've got and the really bright source, which is the sun. The telescope is generally kept around 30 Kelvin, so that's very, very, very cold. I have no idea what it is in Fahrenheit. I don't really work in Fahrenheit very well. 30 Kelvin, wow. How do we 30 Kelvin Fahrenheit? Okay, 30 Kelvin is minus 405 Fahrenheit. So let's just say coldest ever on Earth. Okay, the lowest temperature on Earth ever recorded is minus 135 degrees Fahrenheit. So this is just about three times colder than that.
Layer 1's running about 212 degrees Fahrenheit. And layer 5 on the cold side is running about minus 400 degrees Fahrenheit. So it's approximately 600 degrees or so between the layer 1 and the layer 5.
So this sun shield is a really, 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 really good SPF. It's about 1 million.
There's nothing I can say that can come close to describing how technically difficult this telescope is. We are at the verge of impossible.
This is an engineering marvel. It's not actually necessarily just a scientific marvel, because we've built big telescopes before. I built an 8-meter telescope on the ground. We used 300 tons of steel to build this telescope. Well, there's no way to launch a telescope of that scale into space. The James Webb weighs 6 metric tons. We have to go from 300 tons down to 6 tons. There's no rocket big enough to launch anything this big, so we then have to work out how to fold this telescope up. We had to create this origami telescope. Even the launch has to be perfect. As we launch this thing, the air must actually come out of all those sun shields in precisely the right way. The actual spacecraft must rotate at just the right rate so we don't fry the delicate structures and electronics, because the sun is powering down at one side. And as it leaves the atmosphere, it must be in exactly the right trajectory to actually hit the orbit in the right place beyond the moon. If it doesn't, we'll run out of fuel and this spacecraft will only have 4 or 5 years left. There are over 300 or 400 different operations that have to occur to make this telescope actually come to life. And a huge sunshade has to deploy, which is the size of a tennis court. At this point, things get pretty critical, because now everything starts to cool quickly. So now we've got to get the telescope unfolded before it gets too cold and the joints freeze up. Then we've got to get the mirrors unfolded. We've then got to get the instruments started. And each one of these things has to work perfectly first time. We get one shot to get this telescope right. The slightest thing goes wrong, and this mission could fail.
We lived in Florida, and I could see the Apollo launches from our backyard. We could see them as they cleared the horizon and up into the clouds, then would run inside to look at the black and white television to see the NASA simulation of what was happening. And for me, that was it. That's when I knew that I wanted to be involved in the space industry. We were exploring another world. In the 1960s, another world was the moon. So now this is the opportunity to go and look for planets around other stars. James Webb is going to enable us to look at exoplanets, to observe planets around other stars, to really understand their characteristics. We don't know yet what we're going to discover, but we have the instrument that's going to help us really understand those planets.
Another Earth is undoubtedly out there. In our own Milky Way galaxy, we have hundreds of billions of stars. Our own universe has hundreds of billions of galaxies. To me, personally, it is definitely there. We believe that every star in our Milky Way galaxy should have at least one planet. And we're hoping to find and identify a pool of transiting planets in the habitable zones of small stars. We call it the Goldilocks zone. Not too hot, not too cold, but just right for life. We're betting on the fact that nature delivers, that nature has created many rocky planets, and that life can originate and evolve anywhere given the chance. And we're planning on finding it. The James Webb is going to revolutionize exoplanet atmosphere studies. We'd like to find water vapor because water vapor in a small planet indicates a liquid water ocean. All life on Earth needs liquid water, and it's a great place to start to identify a habitable world. We'd like to see carbon dioxide. It indicates that it's truly a rocky world. But beyond water vapor and carbon dioxide, what we'd really like to find are gases that don't belong. Here on our own Earth, we have oxygen. But without plants and other photosynthetic life, we would have virtually no oxygen in our atmosphere. If we're really lucky, and that would be literally like winning the lottery 5 times in a row. If there are planets around every small star, and there are many, many of those in the habitable zone, and if all of those have life on them, and if that life, half of it, let's say, produces gases, we actually have a shot of detecting that with the James Webb Space Telescope. We have the shot at finding life for the first time in human history with the James Webb Space Telescope.
We push the state of the art because we want to see what's at the outer edges of what's possible. And then we push a little farther.
Okay, minus J mid, MTS full deployment, layer 1.
What's actually happening here is all 5 layers are being tensioned up one at a time, basically 4 quadrants. So we start over here.
What are you guys observing? Anything? What's that noise?
All right, ready to
Clips haven't come out.
plus J2? All right, okay.
Hold that. You just lost the cable.
T-minus 10, 9, 8.
There is big trouble with the $2 billion Hubble Space Telescope tonight.
Grim-faced officials had to reveal that the photo system on board the Hubble telescope is sick.
But Hubble doesn't focus properly.
One of the mirrors on the Hubble Space Telescope was designed to the wrong specifications.
Hubble is actually only 8 minutes away. It only takes the shuttle 8 minutes to get to their orbit. And so you can go fix it. And in fact, astronauts went back several times to do so. The Webb, on the other hand, is 4 times further than the moon, and there's no way to go fix it.
The Hubble orbit is approximately 300 miles above the Earth. The limit that man has been away from Earth in the history of the species, that record is, I think it's about 100 miles or so beyond the moon, which was achieved by the crew of Apollo 13 on their emergency return. That's the furthest away man has been from Earth in the entire history of our species. The L2 point is out here, and that, of course, is 1 million miles from Earth. We don't want to blind ourselves, and this makes us put the satellite far enough away from the Earth so that it's not influenced by the heat coming from the Earth. We're not going in and out of the sun. And so this drives us to orbit the so-called Earth-Sun L2 point, 1 million miles away from the Earth and away from the sun. So we can't afford a mistake, because out at L2, repairman doesn't make a house call. We don't get that second chance. It's a one strike and you're out business. Have to hit the pitch out of the park, all the way out of the park, 1 million miles out of the park.
layer 5 on 3, 2, 1.
Prettier than my imagination. It's really beautiful. This is years in the making. This is hundreds of years of work. I don't think it's possible to overstate how exciting this is.
Wow.
Wow, it looks good.
It looks fantastic.
All right, imagine you are the telescope. Looking out on the universe, looking out on the stars.
We're going to launch this incredibly complex telescope. We're going to pack it up in a rocket, shoot it out, and watch it unfold.
These instruments will eventually travel 1 million miles from us, carrying the dreams and the curiosity of the planet out there.
20 years ago, the planets in our solar system were the only known planets in the universe. It took a telescope to show, in fact, that there are planets everywhere.
It gives us new eyes to penetrate completely unknown regions.
We could have our first shot of actually finding signs of life on another world.
We'll see the first galaxies, the first stars.
We are the only ones like us that we know about, but certainly we're very curious to know if there are others. We're more curious than we have answers, and I think it will always be so.
If we found a planet with life, honestly, any life, it would be very exciting, but the most exciting thing is intelligent life. Can we find them? I think we will. In my lifetime, God, I hope so. Because I want to know, you know?
Through astronomy, we have taken things that were the topic of science fiction and seen them in reality.
When I go and give talks to school kids, I'll tell them that, you know, one of you will be the first person to step onto Mars.
We're going to look up into these beautiful pillars of creation, but actually see creation happen, because we're able to stare through the dust and see the formation of planetary systems and stars. But the real excitement with the James Webb will be the things that we didn't anticipate. Whenever you go into the unknown, you discover things you didn't expect. And those, of course, are going to be the most interesting of all. When they first built the Hubble, there were 4 or 5 things that people predicted they would see. The amazing thing today is if you write down what Hubble's top 10 discoveries are, only one of those 2 of those things are there. We didn't know about dark energy, we didn't know about galaxy evolution, we didn't know about exoplanets. Those were discoveries that the Hubble unrevealed. The James Webb, we don't know what we're going to see, because we've never observed in this region before, to this depth before, and every time we've done this as a species, we've discovered new things. The James Webb Space Telescope is not just a machine built by engineers and scientists. It's taking humanity on a journey